In the last class I had said that atomic absorption is the measurement of absorbance from the free atoms in the environment by electromagnetic radiations. So, the detailed aspects of absorption we will be discussing here. There is certain amount of repetition here, but it is I think it will be good for you. Okay. So, basically what we are talking about is the atomic absorption spectrometry is the measurement of the absorption of electromagnetic radiation by the atoms in the gaseous state. Why gaseous state? Because in the gaseous state most of the free atoms, most of the atoms are and molecules are free. So, they can move about, they can absorb radiation, they can emit radiation and do all kinds of things. So, free atoms do not have vibrational and rotational transitions. This you should understand. Earlier I had told you that molecules will have vibrational and rotational and electronic energy levels, but free atoms in the gaseous state do not have vibrational and rotational transitions. That means they have only electronic transitions. Such excited electron, so whenever we supply electromagnetic energy, they go the electrons are excited from ground state to the higher state, and then they may return to the ground state by atomic emission or atomic fluorescence or atomic absorption phenomena. So, what do we mean? That basically whenever the electrons go to the next higher energy level, we call the whole atom as being present in the excited state. From the excited state, in the vapor phase only, the excited atom can revert to the ground state by thermal means. That means no radiation is given out, or it may give out a radiation corresponding to the different wavelength, longer wavelength and lesser energy, that is known as atomic fluorescence. Atomic fluorescence is also an analytical technique nowadays, and it is being used widely. Several atomic fluorescence instruments are available in the market, and they are being used for multi-element determination of elements in several matrices such as coal and alloys, metals, etc. Or the third part is it may return by atomic absorption phenomena. That means the intensity of the incident radiation is reduced when atomic absorption takes place. So, when they return to the ground state, the energy is lost by the heat, which is not detected spectrally. So, the various states, energy states of an atom are described by quantum numbers. You are all familiar, and then N, L and J, and SPDF you are familiar, but L and other things, these are for the atoms, N, L and J, inner quantum number. So, selection rules say that the orbital angular momentum should be plus or minus 1 and n can be any number. That means, the excitation can take place by plus or minus 1 unit, and it can go to the principal quantum number can be anything. Okay. So, for sodium atom, the most loosely bound electron, there is only one electron in the outermost orbital, and that is defined by 3s2 and s half, that is the electronic state of sodium. So, look at this slide now. I want you to remember the electronic structure of filling the atoms, and here in the outermost orbital there are 2 electrons in 3s2 and 1 electron in the s orbital. Okay. So, this can give rise to 3p2 and p half and p 3 by 2. So, the total angular momentum and the energy states are defined by these numbers. So, from 3 it can go to 3s2, 3s half, it can go to 3p2, p half or p 3 by 2, and then it can go to 3p2, 4p2, these s2 electrons will go to p2, and this can be 1 half plus or 3 by 2 total. So, it can go to np2, p half, p 3 by 2. So, what do we exactly mean in this case is, in emission spectrum all these lines are obtained. What are those lines? 589.593, that is one, and another is 589.996, 2 different states, 3p2 p half and 3p2 p 3 by 2. 3p2 p half corresponds to 589.593 nanometers and 3p2 p 3 by 2 would correspond to 588.996. There is, if suppose if the electron goes to next higher energy state, then that state is defined by 4p2 p half p 3 by 2, and this will correspond to 330.294 nanometers and 330.234 nanometers. Okay. Now, you can imagine that that means the excitation energy for the from 3p to 3 to 4 energy level is higher, from 2s2 to 3p2 is lower than getting it excited to 4p2. That means, the higher you go, higher you want to excite the electron, more is the energy required. So, the resonance line should be always lower, that is what we mean. So, for sodium it is 589.593 nanometers, and the corresponding spin, if it gets added up, it goes to 588.996 nanometers. So, in emission spectrum 3s2 to 3p2, 4p2, np2, all these things are possible. So, in emission spectrum every line, excitation line you will get, except the forbidden lines, but in general you will see that there are several emission lines. Now, I have drawn this here in the figure here, it is electron volts, this is the ground state 3s. So, it can go to 3p low energy, this is 3p half, 3p 1 by 2, this is 3p 3 by 2, and then it can go to 4p, 4s it will not go. So, 3p, 4p, 5p, like that, the amount of energy required also is higher, because at 2p, at around, if it goes to 3p state, the electron volts required is only 2 electron volts, whereas if it is 5p, it is almost 4 electron volts. Okay. That means, almost all electrons in an atom can be excited to higher energy states, and these higher energy states require more and more energy as you try to excite the electrons. But what we are interested is in the lowest energy state, that is 2s2, 3s2 to 3p2. Okay. So, since all elements can be excited to their next higher energy level, in theory any element can be determined by atomic absorption spectrometry, in theory, not always. but there are difficulties. For example, below 200 nanometers, analysis of arsenic, selenium, iodine, sulfur, phosphorus, etc., it is difficult owing to the incipient absorption by oxygen. That means in the vapor phase, what we would come across is not only the free atoms in the vapor state, but also water molecules, oxygen molecules, nitrogen, and several other species will be there. So, all these things have absorption in the absorption range, UV range below 200 nanometers. Most of the molecules, especially air molecules like oxygen, nitrogen, etc., carbon monoxide, carbon dioxide, many of them, they have absorption spectrum occurring in the UV, that is they are all molecular species. But whenever you want to determine any element, you have to get it in the vapor state anyway. So, in the vapor state, if the absorbance line is less than 200, the oxygen also will absorb. So, it will contribute. So, the actual intensity of the radiation would be the sum of the atomic absorption as well as molecular absorption by species like oxygen, nitrogen, etc., nitric oxide, several species are there. So, this is what we mean, that below 200 nanometers it is difficult to analyze, because even though arsenic, selenium, iodine, sulfur, phosphorus, etc., they have resonance lines below 200, but absorption by oxygen and hot flame gases prevent us to get very clear picture. Similarly, there are certain elements like cerium, thorium, and then chromium, tungsten, and several other elements which are refractive in nature. That means they have very high melting point and boiling point. Even if you heat them to 3000 degree or 4000 degree Kelvin, you won't get the vapor phase at all. That means the concentration of atoms in the vapor phase in equilibrium with the solid is very less. So, refractive elements do not lend themselves easily for atomic absorption spectrometry. And what are these refractory elements? They are cerium, thorium, tungsten, vanadium, etc. And these are called as refractive elements. And then of course, you cannot do the atomic absorption spectrometry for radioactive elements, because first of all the radioactive elements are normally short lived, that is number one, and they are all produced under special conditions of bombardment of the neutrons and electrons, etc., on the nuclear targets. So, they are not only short lived, but they are produced only in nuclear reactors, and we cannot the lifetime of the some of the radioactive elements are so short that it does not make any sense trying to determine them by atomic absorption spectrometry. So, what we are saying, basically you cannot do determination of elements below 200 nanometers, that is one of the requirements. It should have a resonance line above 200 nanometers, and then it should not be refractive index, even though this refractive index refractive elements problem can be overcome to some extent, that we will see later as we discuss further. So, another problem is artificial and radioactive elements, they cannot be determined by atomic absorption because of the inherent conditions of the production and short lifetimes. Okay. So, now we will discuss about the thermal excitation. So, how do I get an element in the vapor phase? So, there are several methods. So, we have to appreciate that the atoms, any element you want to determine must be brought into vapor state to produce free atoms. So, it is for atomic absorption to occur, we have to produce a population atoms in the free state. How do you do that? You supply the energy, melt it, and then heat it further, boil it, convert it into vapor state. That is a very standard process to convert anything into vapor. So, we produce a population of atoms in the ground state by exposing a sample of the analyte to high temperatures. So, how do you expose a sample to high temperature? You can put it in the flame or you can simply heat it. How do you heat it? You take a Bunsen burner or LPG gas or something like that, you can heat it, and or you can put it in the flame directly. Take a container and heat it using Bunsen burner or LPG gas until the substance melts. That is not very ideal for atomic absorption spectrometry, but we can also provide by high electric current and all that, electric heating can be done. And at high temperatures prevailing in the flames, what happens? Suppose I introduce it into the flame, not melt it, take it in a pot and then melt it. So, I directly introduce it into the flame. So, the flame temperature will be very high, as we all know. So, the compounds, my sample, analyte sample is usually in the form of a salt. 99% of the time it is in the form of a salt solution. Okay. So, I can solids also we can analyze by atomic absorption spectrometry, but that requires special precautions. 99% of the time we assume that we have an ore sample is dissolved in an acid or alkali or whatever it is. Any sample for that matter to be analyzed must be brought into a solution form, which is there should be a definite relation between the sample weight and the solution form to which it is diluted. So, that solution we introduce into the flame. So, in the flame what we have? Free electrons. Any flame will have a lot of free electrons abundantly available. So, if there are free electrons, if I can produce free atoms in the flame, the electrons can, free ions in the flame, electrons can attach themselves to the metal ions and then convert into free atoms, and that free atom can get excited to next higher energy level. That is the mechanism. So, at high temperatures most of the substances, that is the samples which we normally try to analyze in the laboratory, it may be a jewelry solution, it may be a pharmaceutical solution, it may be a food solution, it may be an ore brought into a solution, like that most of these samples are dissolved and in the liquid form. So, the ions in the flame, the salts vaporize, sodium chloride will dissociate into Na plus and chloride minus ions. Water will dissociate into H2H plus and O2 minus ion. Like that, any other salt present along with the sample will dissociate into ions, which in turn pick up the electrons available in the flame. So, then they produce atoms. This is the only way we know how to produce free atoms in the laboratory. So, the ratio of number of atoms Nj, total number of atoms in the excited state J to the number of atoms in the ground state is given by Nj, that is total number of atoms in the excited state, divided by N0, that is total number of atoms in the ground state. Remember, both the atoms excited as well as unexcited are in the vapor state. So, that number ratio is given by another ratio, that is Pj by P0 into e to the power of minus Ej by Kt. So, here we say Pj and P0 are the statistical weights of the excited and ground state. That means, it is an statistical average of the excited and ground state at that temperature. What is the temperature? T, capital T, that is the absolute temperature, and K is known as the Boltzmann constant, and Ej is the difference in energy for excitation. So, this expression is very important in atomic absorption spectrometry, and this is the starting equation whenever we want to try to convert it into a theoretical calculations. So, Pj by P0 is the statistical weight ratio. This can be determined, this data is available in databases, and Ej is the energy difference that is available by in the experiments and in databases available. K is the Boltzmann's constant, and T is the absolute temperature. So, since this equation is inversely proportional to the temperature, remember T, where is T here? T is e to the power of minus Ej by divided by Kt. That means, T is in the denominator. So, the higher the temperature, more is the concentration. It is inversely proportional to the absolute temperature. Increase in Nj by N0 with temperature is exponential, because there is an exponential term also involved in this, and the higher temperature I produce, the increase is not arithmetical, but it will be exponential. So, if I do it at 2000 degrees particular concentration of the free atoms, at 3000 it may not be double, it may be 3 times 4 times like that. The it is exponential increase, that is what we call it. However, Nj is always small, that is number of excited atoms in the free state, even in the flame, is very very small, even in the flame, compared to the number of atoms in the ground state, that is N0. So, in this expression N0 is always higher compared to Nj. So, that means maximum number of atoms are in the ground state and very few number of atoms, free atoms, are in the higher state, even though the ratio is very less and it is relationship is exponential. Okay. So, Nj we can neglect in that equation, and we can assume that the number of atoms in the ground state is independent of the energy of excitation and nominal temperature of the flame. What we mean here is, in this expression neglect Nj, what happens? So, this it is very less. So, N0 is very high. So, Ej also we assume it to be independent of the excitation energy. That means, in the flame an exact amount of energy is supplied, because the temperature of the flame is always a combination of the gas and oxidizer mixture. Okay, gas is LPG gas, oxidizer is air. It in your homes, here we will use something else, that we will discuss. So, what we are saying is, the number of atoms in the ground state are always higher whatever is your excitation temperature, whether it is flame or not. So, now let us calculate the number of atoms in the cadmium for cadmium in the excited state. So, I am giving you this data, that is the transition is from the N S half to N P 3 by 2. Okay. Transition occurs, this transition occurs at 228.8 nanometers. How do I get this data? It is available in the database. For in the database what it says is cadmium electron can be excited to next higher energy state in the cadmium, and the transition is 1 S1 by 2 to NP3 by 2, and this transition requires occurs at 228.8 nanometers, corresponding electron volt you can always calculate, that is no problem at all. So, now the statistical weightage of the excited to the ground state, that is Pj by P0 is 3. That means, statistically excited atoms are 3 times compared to P0. So, what do we do now? We know the wavelength, we know the Boltzmann constant, we know the velocity of light, and we can calculate the frequency. So, the frequency is nothing but c by lambda, that is 2.998 into 10 raised to 10 centimeter per second, that is the velocity of light, divided by 2.288 into 10 raised to minus 5 centimeter. It is the cadmium excitation energy which I had shown here, but converted into centimeters. Here it is nanometers. Okay. So, this ratio, this quantity is 1.310 into 10 raised to 15 seconds inverse. Now, I can calculate Ej minus E0, the energy difference between the excited to ground state is h mu. So, h is Planck's constant, that is 6.626 into 10 raised to minus 27 ergs seconds, and then multiplied by 1.310 into 10 raised to 15. What do I get? I get a number that is 8.682 into 10 raised to minus 12. Now, this energy Ej, we put it in the equation, in the Boltzmann equation, that is in this equation Nj by N0 we know, Pj by P0 we know, Ej we have calculated, T is the temperature and K is Boltzmann constant, it is also determined. So, putting all these numbers in this equation Nj by N0, what I get is 4.5 into 10 raised to minus 11. So, this is a simple calculation of the ratio of excited to ground state atoms. Okay. So, what does it physically mean? If I supply energy corresponding to 228.8 nanometers to cadmium vapor, what I get is there are 4.5 into 10 raised to minus 10 raised to 11 atoms in the ground state and 1 atom in the excited state. So, what temperature we have taken? We have taken a temperature of 2730 Kelvin. So, you can convert it into degree centigrade. So, minus 273 etc., and then it is almost 2500 degrees. At 2500 degrees there is only 1 atom of cadmium in the excited state compared to 4.5 into 10 raised to 11 plus 11 in the ground state, that is N0 is 4.5 into 10 raised to 11 and Nj is only 1. So, for every 4.5 into 10 raised to minus 11 atoms, there is only one atom in the excited state. These are 4.5 into 10 raised to 11 atoms are in the ground state. Similarly, I can calculate at the hottest temperature of a flame is around 4000 Kelvin, not more than that. The gas temperature which you get at home in your LPG is around 600 to 800 degrees, 600 mostly. And if you use oxyacetylene flame etc., which people use for welding, it may be around 2.5 to 3000. Now, the hottest temperature that can be obtained as a flame is around 4000 Kelvin. So, the population of the atoms in this expression, even if I make it 4000, that is, even if I make it 4000 instead of 2730, I do not get enough atoms in the excited state at all. So, now I give you the sum of the atoms, sum table of the excited to ground state atoms, which we have done earlier for different elements. Now, for cesium, what is the resonance line? 8521 nanometers, that is 852.1, and electron volt is 1.46, and at 2000 it is one excited atom out of 4.4 into 10 raised to 4 atoms, that is 44,000 atoms are there in the ground state and one atom of cesium is there in the excited state at 2000 Kelvin. What happens to 3000? At 3000, for every 1000, 7200 ground state atoms, there is one in the excited state. So, 1000 times less. So, at 4000 Kelvin, I have for every 298 atoms, there is one in the excited state. So, the ratio, as I increase, the ratio of the excited atoms becomes more. Similarly, for sodium, it is 589.0, and the at 2000 it is 1 in 9.86 into 10 raised to plus 6, and at 3000 it is 5 atoms, 1 atom for every 5.8 into 10 raised to 4, that is 58,000 atoms, and at 4000 it will be 1 in 4,400 atoms. Okay. So, similarly, but look at calcium. It is 1 in 10 raised to minus 7, and at 3000 it is 1 in 10 raised to minus 5, and at 4000 it is 1 in 10 raised to 4. Now, compare these 3 data to the remaining 4 data, that is iron, copper, magnesium and zinc. At for iron, what happens? There is at 2000 degrees only one excited atom out of 10 raised to 7 ground state atoms, and of course, it becomes slightly more at 3000 degrees, 1 out of 3.6 into 10 raised to 5, and 4000 it is. But look at iron, what happens? There is 1 in 10 raised to 2.2 into 10 raised to plus 9 atoms, that is 1 million, 10 million, 100 million, 1000 million. One in 1000 million atoms of the ground state, there is only one in the excited state. Similarly, at 3000 it is less. For other elements, copper it is 1 in 10 raised to 10, 1 in 10 raised to 7 at 3000 degrees. So, like that, for magnesium it is 10 raised to minus 11. So, this is how we take a look at this table. So, what does this table teach us? This table teaches us that at any temperature, The ground state atoms are more in thousands and millions than the excited state, which are in 1 or 2 atoms, maybe 4 or 5 atoms. So, this table is very important. We will continue our discussion after a small break. Thank you.